So, imagine a multi-million-dollar satellite tumbling blindly through the vacuum of space.
Right, moving at thousands of miles an hour.
Exactly. There's no up or down, no horizon to look at. And to survive and keep its antenna pointed at Earth, its flight computer has to figure out its exact orientation.
Which means solving thousands of interlocking algebraic equations in, like, a fraction of a second.
Yeah. And if it fails, or if the math is even slightly off, that satellite becomes a very expensive piece of space junk.
And, that level of precision isn't just happening in orbit. The exact same mathematical crisis management is happening right now in the power lines outside your window.
Oh, for sure. And inside the graphics card, the computer you're probably looking at right now.
It's everywhere.
It really is. Welcome to today's deep dive. We are opening up the hood on the hidden mathematical machinery that saves that satellite and actively powers our modern world.
Yeah, today's source material takes us straight into the mechanics of linear systems, the adjoint matrix, and matrix inversion.
And our mission today is to decode this complex alphabet soup of linear algebra. We want to reveal how these abstract equations are the literal structural language of reality.
Which I know can sound intimidating, especially if the phrase linear algebra brings back bad memories.
Oh, totally. But I want to say this directly to you, the listener. Whether you're an aerospace engineer or you're someone who completely avoided calculus, this deep dive is going to give you those ultimate aha moments about how your everyday technology actually functions.
Because the sources reveal a highly elegant, universal system.
Right. So to understand how engineers control rockets or render video games, we have to start at the foundational building block, right? The matrix.
Yeah, the matrix. It's essentially a structured grid of numbers representing a system of linear equations. But to actually use it to solve a physical problem, you have to perform a sort of surgical operation on that grid.
To find what the math calls the adjoint matrix.
Exactly. But before you get the adjoint, you have to build a matrix of cofactors.
Okay, let's unpack this. Because the source material walks through the mechanics, and frankly, deleting rows and columns sounds like a weird mathematical Sudoku puzzle.
It kind of is. Visually, if you have a square matrix, let's call it A, you have to isolate each coordinate.
Right, so finding a cofactor is like looking through a peephole. You block out the immediate row and column to focus entirely on the bigger picture of what remains in the grid.
That is a perfect analogy. You're essentially asking, if I ignore the crosshairs of this single variable, what is the mathematical weight of the rest of the surrounding system?
And the source gives a very specific formula for this, right?
Yes. Finding the cofactor, which they write as C sub ij,
Huh?
it equals -1 to the power of I plus j, multiplied by m sub ij.
Wait, let's break that down. M sub ij is the determinant of that smaller submatrix that's left over when you look through the people.
Exactly. You evaluate the surrounding environment. And the -1 to the power of I plus j part. That just applies an alternating checkerboard of positive and negative signs to the result.
Ah, okay. So it balances the spatial relationship of the data in the grid.
Right. You do this isolation process for every single coordinate, and you get a brand new grid.
Yeah.
Your matrix of cofactors.
Okay, so we have this new grid, but how does that become the adjoint?
Well, then comes the crucial transformation. You take that new grid of cofactors, and you transpose it.
Meaning you flip it.
Yeah, you turn the rows into columns and the columns into rows. And that resulting transposed grid is the adjoint of A.
I mean, that sounds like an incredible amount of computational heavy lifting. Why go through the trouble of building the adjoint at all?
Because it unlocks a fundamental structural property. If you multiply your original matrix A by its adjoint, the complex web of interconnected variables suddenly collapses.
It cleans it up.
Very cleanly. The result is always the determinant of your original matrix A, multiplied by the identity matrix.
And the identity matrix is basically the mathematical equivalent of the number 1, right? It's just a clean diagonal line of ones and a sea of zeros.
Exactly. It represents pure, unadulterated equilibrium. And that equilibrium gives us the matrix inversion formula.
Okay, the holy grail. How does that formula work?
To find the inverse of your original matrix, so A inverse, you simply take the adjoint we just built and divide it by the determinant of your original matrix.
But wait, division is dangerous territory in math.
Oh, very.
If we're dividing by the determinant, we are completely dependent on that determinant being a non-zero number, right? Because if it evaluates to 0, we hit a wall.
You can't divide by 0. It physically breaks the mathematical universe.
Right.
So a matrix with a non-zero determinant is called non-singular. It behaves nicely. It has a unique inverse. But if that determinant is 0, the matrix is singular, and finding an inverse is impossible.
Okay, so we have the mechanics. We isolate variables, build the adjoint, and invert the matrix, assuming our determinant isn't zero. But why are we doing this?
To solve the most universal algebraic structure for real-world problems, the equation AX equals B.
Ugh, the universal problem solver. Let me throw an analogy at this to visualize it. Think of the equation AX equals B as a factory.
Okay, I like.
X is the raw materials, the unknowns you're trying to figure out. A is the manufacturing process, the matrix of rules, and B is the final product.
Right.
So matrix inversion is the process of looking at a finished product, B, and unmanufacturing it by applying the inverse of the process. You're working backward to figure out exactly what raw materials, X, were used.
What's fascinating here is how this factory behaves when things go wrong. The source outlines two distinct cases for AX equals B.
Okay, let's start with case one.
Case 1 is the ideal scenario. The determinant of matrix A is not 0.
So the matrix is non-singular, the factory is working perfectly.
Exactly. The system is consistent.
Yeah.
You get a single, reliable, unique solution. X equals A inverse times B.
We figure out the exact raw materials, but then there's case two. The determinant of A equals exactly 0. Our factory is broken.
Yeah, it's a singular matrix.
So we can't find an inverse because we can't divide by 0. Does the math just give up?
No, it shifts into diagnostics. Since you can't divide, you must calculate the adjoint of A and multiply it directly by B.
So we bypass the division entirely just to see what happens?
Precisely. And this yields two possible physical realities. If the adjoint of A times B does not equal 0, there is no solution.
Wait, no solution at all?
None. The system is inconsistent. In physical terms, it means your final product B could never have been produced by the factory A. It's physically impossible.
Like finding a car that somehow rolled out of a toaster factory just doesn't fit the rules.
Exactly. But if the adjoint of A times B equals exactly 0, the system is classified as dependent.
Dependent meaning what?
Meaning there are either infinitely many solutions or none at all. The equations inside your factory are redundant. You don't have enough independent information to pin down a unique truth.
Which, if you're an engineer building a bridge or steering a rocket, is terrifying. You need a unique solution.
You absolutely do.
And that transitions us perfectly from abstract theory to the physical world. Let's go back to our tumbling satellite, because aerospace engineering relies on AX equals B for basic survival.
Oh, heavily. Specifically in attitude, determination, and control systems.
Right, because flying a spacecraft requires constantly translating between two conflicting perspectives. You have the Earth-centered inertial frame and the vehicle-centered body frame.
And the bridge between those two frames is governed by direction cosine matrices, or DCMs. These are complex rotation matrices mapping aerodynamic forces across the X, Y, and Z axis. That DCM is your matrix A. It's the physical laws of the craft.
And the observable output, RB, is the raw data coming from the ship's sensors, like the inertial measurement units or IMUs and the star trackers.
Right, and a star tracker literally just takes a 2D picture of a constellation. But a 2D picture doesn't tell the computer how to fire a thruster.
It has to work backward.
Exactly. The flight computer has to constantly calculate the inverse transformation matrix. By multiplying A inverse against the raw star tracker feed, it back-calculates spatial acceleration.
It figures out exactly how the craft is oriented in 3D space.
Continuously, just to maintain orbit.
So what does this all mean? I marvel at the universality here, because the exact same mathematical inversion used to parse a star chart in deep space is used to balance the current in a household appliance.
Yeah, the math doesn't care if it's momentum or electrons. Which brings us to electrical engineering and Kirchhoff's laws.
Kirchhoff's current law and voltage law, which are basically strict rules of conservation, right? Current entering a node has to equal current leaving it.
Yes. Energy doesn't just spontaneously generate. And when you apply those laws to a massive multi-loop electrical circuit like a regional power grid, you generate a massive system of linear equations.
AX equals B strikes again.
It does. In multi-loop circuit analysis, matrix A represents the passive elements, the impedance or admittance network. It's every resistor and transformer fighting the flow of electricity.
And vector B represents the active sources, the voltage or current inputs from power plants.
Leaving X as the unknown loop currents or node voltages across the grid. Now imagine a severe summer heat wave. 1 million people turn on their AC units at the same time. Vector B drastically changes.
And you can't just rebuild a physical power grid to test if the wires will melt.
Right. You simulate it.
Yeah.
Engineers invert the impedance matrix, A. By multiplying A inverse by the new heat wave level B, they solve for X, across the entire grid.
That reveals the network's transfer characteristics. They can simulate responses across changing loads and reroute power before a blackout hits.
It's the exact same math.
But it's not just the physical world. This same math is literally building the digital realities we interact with, and it's doing it at an incomprehensible speed.
Yeah. Let's look at 3D kinematics and robotics. Inverse kinematics specifically.
Okay, so if a robotic arm on an assembly line needs to grab an object at a specific 3D coordinate, the end effector, that target point is your B.
But the arm has multiple joints. The computer has to figure out exactly what joint angles are required to hit that coordinate. To do that, it builds a Jacobian matrix.
Which is essentially a sensitivity map of the system.
Right. It maps the velocity at the joints to the velocity of the end effector. And to control the robot, you invert that Jacobian matrix. You solve the system to find the exact angles for x.
But that logic scales up even more dramatically when we talk about 3D rendering pipelines, like in video games.
Oh, absolutely. If you're rendering a game, every object exists in a global model space, but you view it through a specific virtual camera viewport.
So the engine has to constantly translate, scale, and rotate objects to fit your screen.
Which involves computing the inverse or the adjoint of transformation matrices constantly. It's essential for calculating ray surface intersections.
Like figuring out what object a virtual laser just hit.
Yeah, or transforming camera coordinates back to world space to render reflections. If we connect this to the bigger picture, these matrix inversions are executed thousands, if not millions of times per second in graphic engines.
The scale of that computation is just wild. Humans obviously aren't doing this by hand. And relying on the final source node, we see how high-performance scripts actually handle this.
Right, like scripts using Python libraries such as SIMPy.
Yeah, the source specifically notes a 3x3 system in SIMPy, and what's crucial is that it juggles variable symbolic parameters like the letter K alongside generic constants like B1, B2, and B3.
Which is a huge distinction. It performs symbolic mathematics rather than just crunching decimals.
Because if a computer uses floating point decimals to do massive matrix inversions, it introduces tiny rounding errors, right?
Exactly. And a rounding error compounds. It's what sends a satellite off course or breaks a physics simulation.
So by using symbolic parameters like K, the script perfectly verifies the algebra at lightning speed without any floating point drift. It understands the structural integrity of the equation itself.
It's pure mathematical theory fused with high-performance execution.
It really is. Well, to wrap up today's deep dive, we have journeyed far beyond the microscopic math of cofactors and the adjoint matrix.
We saw how that adjoint unlocks matrix inversion.
Which gave us the universal AX equals B equation. And out in the real world, we saw how that equation is actively steering spacecraft, balancing electrical grids, and rendering massive 3D worlds.
The fundamental takeaway for you listening is that mathematics isn't just numbers on a chalkboard. It is the structural language of reality. Next time you play a video game or watch a rocket launch, you'll know millions of unseen matrix inversions are making it happen.
The invisible machinery of our lives. But before we sign off, I want to leave you with a final unaddressed question to ponder, a thought experiment based on the implications of today's sources.
Okay, let's hear it.
If human engineers use systems of linear equations to perfectly map physical forces in space and flawlessly simulate entire digital realities on a silicon chip,
Correct.
could the physical laws of our own universe simply be one infinitely massive, perfectly balanced AX equals B matrix equation, just waiting for us to find its inverse?
Wow. The ultimate decryption key for the universe. That is definitely a deep dive for another day.
Until next time, keep looking for the hidden machinery.